At 14:00 UTC on October 29, 2025, internal tracking logs at the Lowell Observatory recorded an unexpected change in brightness from the interstellar object 3I Atlas. Simultaneously, speed measurements indicated a sudden increase in velocity by approximately 1.2 kilometers per second. Official public reports from NASA released 18 hours later described the comet's brightness and speed as following standard cometary behavior with a stable, predictable rotation. This discrepancy between internal data and public communication remains unexplained. Why was this delay tolerated when standard protocol requires immediate disclosure of significant trajectory changes? 3I Atlas approached perihelion at a distance of 0.25 astronomical units AU from the Sun, traveling at a velocity exceeding 132,000 miles per hour, approximately 113,000 km/h, placing it on a hyperbolic trajectory indicating an origin outside the solar system. As it neared the Sun, photometric data from multiple observatories indicated erratic variations in brightness that did not match the typical sinusoidal patterns expected from rotating cometary nuclei. Instead, the brightness fluctuated unpredictably relative to the comet's speed changes. When 3I Atlas accelerated, its brightness would spike irregularly. When it decelerated, brightness diminished inconsistently. Conventional comet rotation models assert a direct correlation between rotational phase and brightness due to regular illumination of surface features. What mechanism causes these deviations from established rotational light curves? Analyzing brightness variations using data from Lowell Observatory and the U.S. Naval Research Lab revealed amplitude changes in magnitude up to 1.5 within hours, exceeding expected values by a factor of 3. The timing of these brightness shifts correlated with velocity fluctuations measured by radar, ranging from approximately 131,000 to 134,000 miles per hour, an energy variation equivalent to more than 20,000 nuclear reactors' power output over several hours. This implies an internal process modulating both the rotational dynamics and the reflective properties of the object, rather than external solar radiation effects alone. Which internal structure or process could produce such rapid coupled changes? Spectroscopic data from SOHO and the James Webb Space Telescope's NIR SPEC instrument identified atypical chemical signatures in the coma, including heightened levels of C2 molecules and hydrogen cyanide, but with significant temporal variability. Normally, cometary outgassing decreases predictably with solar distance, but 3I Atlas exhibited abrupt fluctuations without clear external stimuli. Ultraviolet observations from NASA's Swift telescope detected hydroxyl radicals in quantities corresponding to water vapor outgassing that varied by a factor of 40 over a period of weeks, dramatically exceeding standard comet evaporation models. Moreover, the usual dusty tail was absent, replaced instead by a diffuse gaseous envelope lacking solid particle scattering. Could these patterns indicate an inhomogeneous internal structure or an irregular release mechanism? Radiation damage modeling spearheaded by researchers at the Royal Belgian Institute for Space Aeronomy suggested that 3I Atlas possesses an outer radiation-processed crust roughly 20 meters thick. This irradiated shell differs chemically and physically from typical solar system comet nuclei, possibly leading to uneven material releases and variable surface reflectance. Such a crust could insulate an inner core, allowing pressure buildups or phase transitions that alter rotation and brightness as gases vent episodically. However, the precise thickness and properties of this crust remain undetermined, and thermal models fail to explain the rapid onset of brightness spikes coinciding exactly with velocity increments. Why do these spikes align so precisely with speed changes if purely driven by sublimation? Parallel observational logs reveal that access to raw telemetry and spectral data was restricted considerably longer than norms dictate. Standard data release protocols for similar comet observations specify public sharing within 12 hours post-event. 3I Atlas data files were held confidential for 72 hours before limited release, with official explanations citing extended calibration needs. Although onboard system calibration logs indicate no anomalies during these periods, this bureaucratic delay coincides suspiciously with peak activity windows. What justifies this threefold excess in withholding potentially critical data? Concurrent with the physical anomaly timeline, internal communications from the ESA Phoebe Task Force indicate the formation of a closed working group dedicated exclusively to 3I Atlas analysis, with meeting records and membership undisclosed. This group reportedly controls all data dissemination and has established new access hierarchies, elevating data authorization from level T2 to T4, effectively excluding many independent research entities and university teams. How does this structural shift in data governance impact the objectivity and openness of ongoing investigations? JAXA's recently installed space-based radar detected minute wobble components in the object's trajectory inconsistent with pure outgassing forces, hinting at possible internal mass shifts or structural changes causing variations in rotation rate. These data were not reflected in NASA's official trajectory updates, which maintained a stable and predictable status. The radar data's release was also delayed without explanation. Why do multiple agencies maintain conflicting trajectory interpretations without reconciling or publicly addressing these inconsistencies? Looking forward, these unresolved anomalies mutually reinforce a scenario in which 3I Atlas exhibits a complex internal dynamical structure not accounted for in existing cometary models. If brightness variations are correlated intricately with rotational acceleration, this suggests coupling between nucleus morphology and volatile release patterns. The absence of dust, combined with delayed and restricted data disclosures and interagency communication lapses, elevate questions about potential informational suppression or precautionary control measures. What mechanism inside this object produces synchronized brightness and velocity changes? Why do institutional protocols deviate so markedly from standard procedures? How do these discrepancies affect the scientific community's ability to develop accurate models? The coming weeks are crucial as 3I Atlas continues to retreat from the Sun, maintaining observable brightness and rotational irregularities. Observational persistence is the only path to resolving whether these patterns will dissipate naturally or reveal deeper structural peculiarity. Pondering the implications, could an unknown internal mechanism explain the rapid fluctuations, or does this point toward a non-standard object type? Why is the scientific dialogue fragmented, with public statements diverging from recorded telemetry? Does this represent a failure of current observation frameworks or a predetermined effort to control narrative dissemination? The confluence of physical and informational anomalies constitutes a crisis point in understanding interstellar visitors. Clarity demands transparency and comprehensive data sharing. Until then, the true nature of 3I Atlas remains a question open to rational inquiry and meticulous verification. At precisely 13:45 UTC on October 31, 2025, photometric equipment at the Lowell Observatory recorded a critical shift in the brightness profile of 3I Atlas. Unlike the steady rotational light curves typical of comets, this object's luminosity exhibited erratic oscillations, varying by nearly a full magnitude within intervals as short as 2 hours. Simultaneously, Doppler radar data captured by the U.S. Naval Research Laboratory indicated an unexpected acceleration spike from 130,000 to 134,000 miles per hour. The physical correlation between rapid velocity increase and irregular brightness pattern deviation contradicts conventional comet rotational dynamics, which predict brightness fluctuations aligned clearly with rotational phase and uniform spin rate. Scientific consensus anticipates comet nucleus rotation as a rigid body spin modulation, generating predictable periodic brightness variations as illuminated surfaces reflect light. Contrary to this, 3I Atlas's brightness does not peak or trough in synchrony with rotation markers. This dissonance strongly implies internal processes influencing angular momentum, such as non-uniform outgassing or shifting mass distribution. The scale of these variations compares to energy outputs on the order of 20,000 U.S. nuclear reactors when viewed as integrated over time and spatial extent. Analyzing spectral data from SOHO's ultraviolet coronagraph and JWST's near-infrared spectrograph reveals unanticipated chemical diversities. Significant C2 molecular emissions persist alongside non-radial emissions of hydrogen cyanide and hydroxyl radicals, markers for water vapor and organic active species. The intensity of these emissions fluctuates independently of solar proximity, contradicting sublimation models based on irradiance alone. The lack of a dust tail, verified by coordinated SOHO Stereo GOES observation campaigns, remains unexplained by traditional particulate release mechanisms. The prevalent hypothesis involves a CO2 ice mantle inhibiting erosion of water ice, but the sudden disappearance of this mantle shortly before perihelion and subsequent burst of outgassing remains unaccounted for in peer-reviewed models. Importantly, telemetry data access and release reveal procedural anomalies. NASA's standard practice prescribes raw spectrometry files posted publicly within 12 hours following event triggers. Data concerning 3I Atlas were quarantined for 72 hours, with the publicly stated reason being instrument calibration delay. Yet internal system diagnostics logged routine operation during this period. This extended blackout overlaps with the time window corresponding to peak anomalous activity and irregularities in brightness and velocity. Why was there no contemporaneous explanation or transparency in data release? This delay exceeds standards by a factor of 6. Within institutional circles, ESA confirmed the establishment of a high-level embargoed Phoebe working group tasked specifically with managing all information flow and analysis concerning 3I Atlas. Membership rosters and meeting transcripts remain confidential, and data access has been reclassified to a higher security tier, T4, restricting previously authorized university and independent researchers from real-time analysis. This represents a shift from the open access protocol typical for solar system minor bodies. Does this centralization serve scientific rigor or informational control? Further interrogation of JAXA's deep space radar returns indicates subtle non-gravitational perturbations inconsistent with symmetrical outgassing alone. Minor wobble components recorded suggest dynamic internal mass redistribution or unknown structural alterations influencing rotation. These signals have not been incorporated into NASA's public trajectory updates, which maintain a nominal stable path report. The discrepancy between agency reports amplifies uncertainty. Why are conflicting trajectories not reconciled publicly? The combined data point toward a complex internal mechanism modulating both rotational state and reflective properties. The object's unusual brightness-speed correlation may signify episodic venting or phase transitions within a non-homogeneous nucleus, possibly layered or containing exotic materials. Lacking dust tail and volatile outbursts misaligned with solar radiation effects imply internal irregularities rather than surface-driven phenomena. The lack of open data sharing impedes the scientific community's ability to develop or falsify models adequately. Independent researchers emphasize that until unrestricted data access is restored, the true nature of 3I Atlas's anomalous behavior remains masked. The question remains, does internal structural complexity alone account for these observations, or does this point to unacknowledged phenomena? The clock continues to run. As 3I Atlas recedes from perihelion, ground-based observatories worldwide prepare for months-long campaigns to monitor its fading activity. Yet, critical gaps in data availability persist, alongside contrasting institutional narratives. These conditions foster an information environment ripe for speculation, yet lacking clarity. The unresolved juxtaposition of physical anomalies and bureaucratic opacity compels reflection. What critical data remains undisclosed, and why? What are the potential implications if these irregularities herald phenomena beyond current scientific paradigms? At 1623 UTC on November 6, Anunsai 25, data logs from NASA's Swift UVOT instrument recorded a persistent emission of hydroxyl radicals from 3I Atlas's coma, indicative of water vapor release at rates of approximately 5.7 10^28 molecules per second. This rate represents a 40-fold increase compared to the same period 1 month earlier, far exceeding the typical sublimation scaling expected from standard cometary physics near perihelion. Notably, observations from the SOHO and Stereo missions corroborate this water outgassing anomaly, but simultaneously report a conspicuous absence of the traditional dusty tail expected at such activity levels. Standard comet morphology predicts that sublimated gases entrain significant dust particles, creating observable tails extending millions of kilometers. 3. Atlas's lack of dust challenges these models, suggesting either an intrinsic compositional difference with a notably depleted dust reservoir, or a surface or internal process restricting dust ejection. The explosive brightness increase within days of perihelion without accompanying dust phenomena departs from models based on solar system comets, emphasizing a potentially unique internal structure. Further spectral data reveal fluctuating emissions of C2 and cyanogen molecules, substances commonly linked to organic ices. The fluctuating chemical signatures, combined with abrupt brightness changes synchronized with velocity spikes exceeding 1/200 meters per second increments, underscore an active internal mechanism influencing both mass release and rotational dynamics. This relationship contravenes expectations of uniform rotation-driven brightness modulation, pointing toward episodic outgassing events likely linked to internal structural heterogeneities. Access to corresponding telemetry experienced notable delay anomalies. Unlike the 12-hour maximum data latency protocol established by all major space agencies for near-Sun bodies, 3I Atlas radiometric and spectral data remained inaccessible for 72 hours post-event. Official statements cited extended calibration, yet internal technical logs indicated nominal instrument performance. This prolonged embargo coincided with the comet's peak anomaly phases, raising questions about intentional data withholding and whether the delay was to enable review of unexplainable features. Simultaneously, ESA confirmed creation of the Phoebe Group, a classified consortium charged with 3I Atlas monitoring and data gatekeeping. This group's composition is undisclosed, and data access level changes have barred many academic researchers, transitioning public protocols to a tightly controlled information hierarchy. Institutional transparency is undermined, restricting external validation and wider scientific scrutiny. How does this extraordinary governance shift a line with international scientific norms? Radar data from JAXA's newly commissioned spaceborne system detected angular momentum irregularities inconsistent with symmetrical outgassing models. Minor but measurable rotational wobbles, not reflected in NASA's public trajectory prints, signal potential mass redistribution within the nucleus or extrinsic torque effects. Given these contrasts, why are such crucial data obscured and not reconciled with the public narrative? The aggregate evidence strongly supports a model where 3I Atlas harbors a layered or otherwise structurally complex nucleus, with active internal processes driving coupled brightness and velocity changes. Its unique radiant signature in absence of dust, alongside delayed and restricted data releases and interagency communication inconsistencies, imply possible informational control or precautionary obfuscation. Does this point to unknown physical phenomena or an engineered origin? How reliable are current cometary models when applied to interstellar objects presenting such departures? The imminent fading of 3I Atlas from observational reach stresses urgent continuous data collection and openness. Institutional opacity in the face of these anomalies fosters doubt and demands further inquiry to decode the true nature of this visitor.